All right, my name is Gary Johnson, and I'm an old retired guy. I had two careers, and I was kind of forced into that.
Pardon me, sir.
Yes.
I would ask you to stand about here because there's a camera and we have about 20 or 30 people on the internet also trying to watch you.
I see.
Thank you. I
Okay.
appreciate that, sir.
Thank you.
All righty. Well, I had two careers. One was in aerospace defense for about 20 years, and then I was laid off from that by a plant closure at a time when the whole industry was contracting. So I had to go do something else for a living. And so I did civilian stuff. I did a little civil engineering. I did a lot of teaching, finally hit retirement age and retired. And as you can tell from my accent, I'm from Texas. I live on a cattle ranch. And I'm still farming cattle and killing prickly pear cactus. I even invented a way that you can get rid of it and you don't have to pick a single piece up. It just kills it. All you have to do is drive around on a tractor drinking beer. Okay, so that's the kind of person I am. I started out in the slide rule days. All of us, everyone around me, when I first went to work, we were still doing rockets and ramjets with slide rules. I don't adapt real well to the very modern technologies, but I did learn how to do a little bit of PowerPoint. Now let's see if I can get my notes here, because I got to skip some slides in this one to make this work. All righty. We'll skip all that and go down here to number 3. There we go. Now here's the problem. You've got some competing requirements with the atmosphere you need to breathe in some kind of a space habitat or a spaceship, whatever you have. And you've also got to be able to go outside in an oxygen suit and do stuff outside, EVA stuff. Okay. You kind of like a simple atmosphere inside your habitat. You're talking about a mix of oxygen and nitrogen. You could use a reduced pressure and up the oxygen percentage a little bit. And we've been there before. It works. But you have to avoid all the hypoxia and long-term health problems, so you can't take this to an extreme. All right, now, what you would also like to have in order to make this more practical for doing the work you got to do outside, you'd like to get rid of that you'd like a no pre-breathe situation so you can just don the suit, go through the airlock and go outside. They can't do that on the ISS right now, and they couldn't do it on the shuttle. They had to pre-breathe to blow off the excess nitrogen so they wouldn't get the bends going outside. And if you ever learned anything about scuba diving, you know what the bends are. It can kill you. It's very painful. We'd kind of like to make lower pressure spacesuits feasible, not the higher pressure ones. We started out, the NASA suits that we started out on Mercury and Gemini and Apollo that we used all the way through Skylab were 3.7 psi pure oxygen suits. They were restrictive enough. The suits went to higher pressure. They got more restrictive. They were 4-something on the shuttle. They started out 4-something on the ISS and were headed in the direction of 8 psi suits. They don't bend well. You're working hard just to move around. How do you accomplish a job out there? It's getting very difficult. You can't do that if you have a job to do in space, or especially on the surface of another planet, like the moon, Mars, whatever. We got to go the other way. We kind of like a lower pressure suit because it's a lot more flexible. It's easier to do the work. It's less bulky. You're just better off. Okay. So I'd kind of like to make what they call mechanical counterpressure spacesuits feasible once again, because the high pressure has ruled that completely out. Now, there's been 2 efforts on that. One goes all the way back into the 60s. There was a mechanical counterpressure suit prototype that was tested in the late 1960s. It was intended for Apollo, but they didn't get it done in time to go to the moon. That helmet and oxygen only backpack and basically 7 layers of pantyhose weighed 85 pounds. And you could climb a ladder, you could crawl under these chairs, you could go wherever you wanted to go, bend over backwards. It was flexible. And it was tested in a vacuum chamber at 87,000 feet equivalent for 30 minutes. So if there was a problem, we'd have known about it by now. But that one never went anywhere. And it was looked at again by Dava Newman at MIT before she went to NASA. And the higher pressures have pretty well kind of ruled that out, because you need a low pressure suit to make that work. You got to worry about fire danger. You go to higher oxygen content, like you're breathing hospital air, hospital oxygen, 40% oxygen. That'll accelerate the fire danger. Makes the fire burn faster. It's harder to fight. You have less time to get clear, whatever. Okay. Now, if you lower the pressure, that also deaccelerates the fire. All right. So you got to worry about fire danger. And you still want to be safe, both in your habitat and in your spacesuit, if the pressure should leak down 10%. You don't want to start incurring hypoxia just because you're a little bit under spec on pressure. All right, so we got to worry about all those things. Now, let me see. I'm going to skip a bunch of them down here and go to number 7. This is 3, 4, 5, 6, 7. There we go. Now, there's 2 kinds of hypoxia here that we got to worry about. One is kind of short term. This is what everybody's familiar with. And you can kind of use the human experience that we have with pilots' oxygen masks that relate to short-term hypoxia issues, right? Because that's a thing where you're breathing pure oxygen. It's vented to the local atmospheric pressure. This is not pressure breathing. It's vented. It's basically pure oxygen. It works pretty good for an all-day mission flying an airplane at 40,000 feet. It's a little iffy at 45,000 feet. And we've had some pilots that have been above 50,000 feet on nothing but an oxygen mask. But it's a zoom climb. They're only up there for several seconds. Okay. So somewhere around that 40, 45,000 foot level is your limitation on what you can do for low pressure breathing with pure oxygen. That's human experience. Okay, now for long-term hypoxia, you got to look another way. This is not something you do for a few hours, then you go back inside it so that you can do it again the next day. If you're inside, you need to be breathing that 2-gas mix, and you got to worry about not short-term hypoxia, but long-term hypoxia and other health effects. Okay, and I ran across this article that's on the slide here about some research they were doing about the occurrence of chronic mountain sickness, classic long-term hypoxia, in populations living in mining towns in the Andes, all the way up to 14,700 feet. And half the people in the village showed symptoms. Some other towns, a little bit lower elevation, a little bit less percentage of the population, and there's a lot of error here. So I've got big error bars on my data on that plot. The lower down you are, the lower the percentage of people that show chronic mountain sickness. And you get down, there's a certain critical altitude below which nobody has it. And that critical altitude is 2,500 meters, just under 9,000 feet. Okay? So Earth equivalent, if you're breathing 21% oxygen, up to about 8,000 or 9,000 feet, which is also about the cabin pressure altitude they put in an airliner, you don't get any problems with chronic mountain sickness, long-term hypoxia. Okay. That same article mentioned the Spanish colonization experience in South America. When the Spanish were trying to settle in that region around the Andes, they noticed something. And there's always been childbirth problems in previous centuries because medicine was pretty primitive. 10 or 15% troubles all the time, at least, sometimes worse, and a lot of it was fatal. But when they tried to settle at altitudes above about 2,500 meters, the rate went up. Below 2,500 meters, they couldn't hardly tell it from living at sea level. They couldn't tell any difference in the rates. Funny, it's the same altitude. So there's some kind of relationship between reproductive problems induced by hypoxia and the human response to hypoxia, and it all centers at about 2,500 meters. That's pretty good data. All right, let's see here. Where do I go next? Now, I'm using a kind of a crude model for some of the calculations I made. Not everybody agrees with it. A lot of people use something called the alveolar gas equation, and I didn't use it, and there's a reason for that. You see the first term in that equation up there where it says VF with a subscript on O2, volume fraction O2, and there's a difference in pressure there. There's the atmospheric pressure, and that's the water vapor pressure at human body temperature. That term models the displacement effect of having water vapor inside your breathing passages. They're wet. That's equilibrium, but yeah, it's in there long enough. You're coming close enough. It's a good model. Okay. The second term out there that's tacked on behind, that models the displacement effect of the CO2 that's coming out in your lungs. And there's a problem with knowing the right numbers to put in the equation. The equation is trying to tell you how much oxygen it gets into your blood. But you got to know how much carbon dioxide is coming out of your blood. And there's a funny thing going on there. And it's, again, it's that same critical 2,500 meter altitude. The human response to hypoxia changes suddenly from holding a constant CO2 percentage in your blood and letting the oxygen concentration float. It does that between sea level and about 2,500 meters. And past 2,500 meters, the body changes. Its strategy is different. I don't know how this works. I'm an engineer. I just know what I've read. It goes to maximizing the concentration of oxygen in the blood, and CO2 starts to fall because you're going into hyperventilation. And the higher you go, the more you gasp for breath, and you start to go into what's called respiratory alkalosis. The pH of your blood goes alkaline. And the higher you go, the sicker you get. People using this equation to design spacesuits are plugging in the sea level numbers, and the equation is lying to them because it tells you that the mountain climbers that are climbing 18 and 20,000 foot mountains without oxygen can't be able to do that. That's what the equation says if you plug in the sea level values. But the body is changing, and there's no agreement in what numbers to plug in if you're above that 2,500 meter equivalent. So I didn't use it. I used the first term. I was using that. You could just as easily look at the partial pressure of the oxygen in the breathing gas mixture that you're looking at. It doesn't matter so much what the model is. You can use any of these models. You got to plug the right data in that one, or you're going to get the wrong answer. The other models are simpler. You're not going to have that problem, garbage in, garbage out problem. What's critical here is the criteria that you're using to constrain and limit what you can do. Now, they need to be cast in the form of the model that you're using so that they're consistent. That's all you have to worry about. Just use human experience. So I didn't use that one. I used something else, but it doesn't matter. You're going to get about the same answer almost no matter which way you do it if you use the human experience constraints correctly. Now let's see here. Suit pressure experiences. I think I already told you about that. The pilot oxygen mask experience at 40,000 feet would be equivalent to being in a pure oxygen suit at 2.7 psi. We haven't been that low. We've been at 3.7 all the way up through Skylab. It worked fine. This is for the spacesuits now. There is one other problem that you're going to run into, and that's if you get below about 3 psi and you're there for a long time, maybe all day long, your lung tissues are going to tend to want to dry out and crack. So you don't really want to go below about 3 psi. But the oxygen mask experience, which is only like 8 hours flying the airplane or something like that at the altitudes like that, unpressurized, that worked even at 2.7. But something near 3 psi looks pretty reasonable. That's Paul Webb's suit. That guy's wearing 6 and 7 layers of pantyhose material and nothing else. That oxygen backpack is nothing but oxygen makeup. There's no air conditioning system there. He doesn't need it. He sweats through the porous garment directly into the vacuum, the same way we sweat through our clothes here in this room. That's how the body stays cool. All right, and a little helmet tied to that suit so he can breathe. He's pressure breathing. That's 3.3 to 3.7 psi. And like I said, it was tested way back in the 60s, way above the vacuum death point, which is nominally about 60,000 foot equivalent. And he was in there on a bicycle ergonometer, 30 minutes pumping and doing work. If that was a problem, we'd know about it. It only takes about 20 minutes for a hand exposed to vacuum to begin to swell. Okay, it only takes about 20 minutes. We'd know. Let's see. That's a pretty supple suit too. I'm going to skip 11. Let me go to. All right. I was using the wet in lung partial pressure. That's with the water vapor displacement. You could use the other model. It really doesn't matter. It's part of the alveolar gas equation. I'm not afflicted by the unknowns or the garbage in, garbage out problem. Kind of discussed all of these things. Let me move on. Otherwise, we're going to run out of time. Other criteria. Fire danger. I'd really like to put a constraint on what this habitat atmosphere can be so that we don't aggravate the fire danger. And basically, I conceptually used a 2-component, 1-step Arrhenius reaction rate model as my concept behind the fire danger criterion. There'd be a concentration of the fuel raised to a power that's somewhere near 1. There'd be a concentration of the oxygen that's raised to a power that's not far from 1. And the sum of those is the order of the reaction, which is about 2 for most combustion reactions. It's got a coefficient out front that relates to the rate, and it's got an exponential temperature factor. Temperature increases, raises the rates. Well, I looked at that and I thought, what's driving the fire danger here, regardless of the fuel we're talking about, is the oxygen concentration. Now, that's related to the oxygen partial pressure. It's also related to the total pressure. Okay. So the total pressure and the temperature give you the density. And if you know the mass fraction of the oxygen, the mass fraction times the density is the oxygen concentration in mass per unit volume, kilograms per liter, or kilograms per cubic meter, whatever. Okay. And I worked what that was for sea level air at 77 Fahrenheit or 25 C, and it's 0.275 kilograms per cubic meter. So any atmosphere that we have, if it stays under that, the fire shouldn't burn any faster than it does what we're used to fighting in sea level warm air. That's another constraint to put on this. Okay, now for the pre-breathe, there's the Navy was using some criteria for its 2 and 3 gas mixes for deep sea divers, and NASA got onto that and they modified it to use for getting from a 2 gas mix down to a pure oxygen suit at low pressures. And basically, it's the partial pressure of nitrogen in the 2 gas atmosphere that you're leaving, divided by a factor of 1.2. What happened here? What did I do? I don't know there, come back. Okay, good. Let's see if we can get back where we were. There we go. You divide that partial pressure by 1.2, your suit needs to be at least that pressure of pure oxygen to avoid the pre-breathe requirement. It can be higher, but it can't be any lower. If it's any lower than that, you need a pre-breathe. You got to blow off the nitrogen or you're going to get the bends when you go out to airlock. It's that simple. So I've got a fire danger criterion. I've got a pre-breathe criterion. I've got a short-term hypoxia criterion based on oxygen mask data. And I've got that study of high altitude peoples for the long-term hypoxia, that 2,500 meter criterion. All right. So that's what I based this analysis on. Now I did this way. One study was to look at the lowest pressure suit that we could meet the short-term hypoxia criteria with. And that turns out to be about 2.7 or 2.6 PSI. You could even leak it down all the way to 2.4. But if it's leaking down, you better get inside because you got a problem. You got time to get inside. If you stayed out more hours, you might start losing some cognition. But those low pressures, breathing pure oxygen on an oxygen mask, is sufficient cognition to fly a combat mission in a high altitude jet aircraft. We're not talking about impaired cognition here, even at these low pressures. All right. Now on the other branch over there, let's look at the habitat atmosphere. I'm not worried about the short-term criteria with it. I'm worried about that long-term criteria. What's the oxygen content that's reaching the lungs as a function of percentage oxygen in the mix and the total pressure of the mix? That's the two variables I have to play with. It's how much oxygen is in the mix and what's the total pressure in the hab. And I got to worry about it, even if it's leaked down 10%. Okay. And then I'm going to come together and compare and make a recommendation. Let's see where I go next. Other criteria methods. All right, we got that. Yeah. I think we already discussed this a little bit in the definition that I'm using with just water vapor displacement. I had some numbers here and I picked out of the three there, I picked the two top ones. And I made the standard suit design at the higher value, and the 10% leak down couldn't violate the middle value there. So it's that simple. That's based on how that calculates out behind that oxygen mask with just water displacement. Somebody using the AGE with the right CO2 data would get a slightly different number, but he'd also be calculating slightly different numbers. They're consistent if you do it the same basis. It doesn't matter. Okay. And long term, I set it to that 25, whatever the oxygenation, whatever it is for your two gas mix as a function of the mixture and the total pressure. I don't want it to go below the oxygenation that you get at 2,500 meters, even when the hab is leaked down 10%. So my design pressure is 10% higher than that. Okay, it's not a big deal. Now let's see if I can. I'm going to skip that. We already talked about the fire criterion. This is what I got for the min suit study. I had a preferred suit and a min acceptable suit. And the preferred suit, the design pressure is just barely under 3 PSI. It's close enough to 3 that I don't need to worry about drying out the lung tissues, causing cracks and bleeding. Okay. But leaked down to 2.67, he's still got the cognition. He just needs to go inside and get the suit fixed. It's not a big deal. Now, it doesn't matter what kind of suit you're talking about, a pressure suit or one of those MCP suits or a partial pressure suit. It really doesn't matter. It's the same criteria for all of them. Okay. You can wear that suit or anything higher and there's no pre-breathe. Okay. The min acceptable is a little bit lower. Like I said, leaked down, it could be as low as 2.4 and you're good for maybe an hour before the cognition starts to deteriorate a little bit. All right, I did a whole lot of habitats. I violated some of my criteria there slightly, the ones that are highlighted in yellow, but I picked the min acceptable suit design for my hab atmosphere so that any suit that I really want would be higher than that. I don't have to worry about a pre-breathe criterion, even if it was only a 3 PSI suit. Okay, so I looked at a lot of them and chose one. And there it is. The design pressure, for those of you that like PSI, where is that over there? Can't read it. Maybe I can read it here. 6.172 PSI, and it is 42%, excuse me, It is, I think it was 42% oxygen. It's not that much different from hospital, except it's lower pressure, and that cuts the fire danger down. The lower pressure does. It also cuts down the nitrogen pressure, which gave me that low feasible suit pressure for no pre-breathe. Now, we've been there before, almost, with Skylab. Skylab was a 5 psi atmosphere at 74% oxygen. It violated the fire criterion a little bit. Okay, they didn't use pre-breathe for the suits. They went outside in that 3.7 psi suit, never had a problem with the bends. We've been there. So we need to be looking at that to make these more advanced spacesuit designs and more flexible spacesuit designs feasible, so that we don't have to spend an hour or 2 or 3 waiting in the airlock before we can go outside. So doing this kind of study solves a world of problems with making this more practical. I don't know. Is there any questions before we run completely out? Yes, sir.
So I know you talked about gas pressure and mechanical counter pressure, but I was just considering the idea of like, what are your thoughts on the feasibility of like a hybrid of gas pressure and mechanical pressure?
That would work too. I think there have been experiments along that line, and I think they've been talking about I may have this backwards. I thought they were talking about a gas pressure glove and a mechanical counter pressure suit, and they've done some experiments with that. I don't know how extensive the experiments were, or if they went as far as what Dava Newman did or what Paul Webb did. Okay, now I'm old enough. My dad knew Paul Webb. My dad was also an engineer like me. So yeah. Yes, sir.
Higher pressure environment for the suits. What was the original condition?
They were plugging in sea level values of blood CO2 concentration into the alveolar gas equation, and it was lying to them. They thought they needed more suit pressure in order to get enough oxygen not to suffer a cognition problem. But everybody was ignoring the oxygen mask data.
Experience given enough data that was fine.
Most of the guys that knew about Skylab are now either long dead or long retired. That's another problem that's been going on here. I've been around long enough. I saw this stuff. I was 7 when Sputnik was launched. So, yeah. Yes, sir. Up about 2,500 meters.
What is PSI?
DSI.
Yeah.
Oh, the PSI? I don't have it in the top of my head, but it's air pressure it'd be around 10 or 12 PSI. Yeah. See, I went to a lower pressure, but I raised the oxygen concentration to get the same oxygen supplied to the lungs. And I did it without violating the fire criterion. And I did it low enough to show no pre-breathe for a very low pressure suit. You could go back to what we were using on Gemini and Apollo, and this would work fine. And those were more flexible suits than we're using today by far. So, yeah.
Perfect. Well, we're out of time, but thank you very much.
You bet.